This is a Satellite Foundation course for GOES-R training on baseline cloud products. My name is Scott Lundstrom, and I will be describing these products that were developed by Andy Heidegger and Mike Pavlonis from NOAA-STAR, Patrick Minnis from NASA Langley, and Andy Walther at SIMS. The subjects of this GOES-R baseline products training are the different cloud products boxed in yellow. There are a lot of them, and some, chiefly the cloud mask, have a big influence on other products. Learning objectives for this training are listed on the left. You'll learn which ADI bands are used for the products, how the products are produced, there is a specific order, the temporal and spatial resolution, and some sample uses and limitations. GOES-R baseline cloud products are listed on the right. These are the products that are available in AWIPS. This flow chart shows the order in which the products are computed. Cloud mask is computed first, then cloud type and phase, then cloud top parameters, and then cloud optical properties. If you see something suspicious in a cloud product, or in a product that might rely on cloud clearing, step 1 should be to examine the cloud mask. It's not perfect, and it can cause errors and downstream predictions. In the case above, if cloud masking is wrong, it can introduce errors into every variable within the dashed red box. To repeat, there is an order to how the cloud products are created. Each builds on its predecessor, or requires information from the predecessor. Clear sky mask is produced with every CONUS image, and an example is shown here. Clouds are denoted as white, clear regions have missing values and are transparent. Note the region over Virginia, circled in yellow. Clouds are not apparent in the visible imagery, but they are in the 1.38 micrometer cirrus channel, so the clear sky mask is correctly identifying this region as cloudy. The clear sky mask is computed for every image in full disk, CONUS, and mesodomains. It has 2 km resolution. The default is clear, and the algorithm seeks evidence of clouds. It is produced out to a local satellite zenith angle of 70 degrees. There are known limitations with the cloud masks, chiefly at high zenith angles, that is near the limb, over warm clouds, and in coastal regions or near the terminator, which is the divide between day and night. Which GOES-R bands are used to create the ABI cloud mask? In the visible and near infrared, the visible at 0.64 micrometers, the cirrus channel at 1.4 micrometers, and the ice channel at 1.6 micrometers are used. The infrared channels include the 3.9 micrometer channel, the low-level water vapor at 7.3 micrometers, the 8.4 micrometer channel, and the 11.2 and 12.3 micrometer channels. Cloud mask is computed up to a satellite zenith angle of 70 degrees, which is shown graphically here for GOES West and for GOES East locations. Some cloud products computed subsequent to cloud mask are not computed all the way out to the satellite zenith angle of 70. They cut off at 62 or 65 degrees. Once cloud mask is computed, cloud type, as shown here, is computed. Cloud type is a future capability product. It is not baseline and it is not available in AWIPS, but it is used by subsequent products. Cloud type is a way to identify cloud layers and cloud types. The baseline product associated with cloud type is cloud phase. Cloud phase is produced every 15 minutes for full disk, every 5 minutes for CONUS, and every minute for mesodomains. It's computed out to a local zenith angle of 65 degrees, and only uses infrared bands to avoid day-night discontinuities that would arise if reflectance bands were used. The baseline product, cloud phase, is available in AWIPS, and it includes 4 separate categories: warm liquid water clouds, supercooled liquid water clouds, mixed phase clouds, and ice phase clouds. Here's an example showing visible imagery on the right and the cloud phase product on the left. Cloud top height, a baseline product very useful for aviation, is computed for every full disk, CONUS, and meso image. For full disk and CONUS domains, the product has a 10 km resolution. This means a 5 by 5 pixel footprint is used, and the best 2 km pixels within the footprint give the information. In the mesodomain, there's 4 km resolution, that is a 2 by 2 pixel footprint is used. Height is computed using bands 14, 15, and 16, that is 11.2, 12.3, and 13.3 micrometers, and it requires the cloud mask and the cloud phase. It does not necessarily give a good answer with thin cirrus. Thin cirrus is a problem for many cloud products. Cloud top pressure, a baseline product that is also used in aviation, is derived simultaneously with cloud top height and cloud top temperature. It is computed for all full disk, CONUS, and meso images, and has 10 km resolution at full disk and CONUS domains, and a 4 km resolution in meso domains. This is the same temporal cadence and horizontal resolution as cloud top height. Forecast model temperature profiles convert cloud top temperature computed to cloud top pressure and cloud top height. ACHA variables are computed using bands 14, 15, and 16 on ABI, that is 11.2, 12.3, and 13.3 micrometers. Cloud top temperature is also baseline, and it's a product that is used in other products because it generally gives a more accurate value than individual channels. It is computed in concert with the cloud top height and cloud top pressure as part of the ABI cloud height algorithm ACHA. The temporal cadence and horizontal resolution is shown. Cloud top temperature is computed for every full disk image and for every meso image. It is not computed for CONUS domains. Here's the same slide, but the default color has been changed so that the coldest temperatures are blue. Don't be afraid to change color tables. Save them and then load the products as part of a procedure. Here's a reason why you might want to use the cloud top temperature product. Which band would you use for a cloud top temperature? There are 4 good window channels on ABI. Which one is best? For the 10.3 and 11.2 micrometer channels shown here, look at the cold cloud top circled in yellow. It's a slightly different temperature. If you need a threshold temperature for an algorithm, that can make a difference. In addition, if you're looking at brightness temperatures, it's hard to compare the legacy GOES window channel to current ABI channels because the width of the heritage channel is different than the width of the ABI channels, and the central wavelengths are different as well. Here's an example that shows brightness temperatures for 4 window channels on GOES 16 for developing cumulonimbus cloud, that's circled. Brightness temperature values are close but not exact. If you are using a threshold of -44 Celsius, for example, there are values on either side. Brightness temperatures differ by 2 to 3 Kelvin between the bands. Note that the cleanest window, the 10.3 micrometer, is the warmest, as expected. This is the same scene but 1 minute later. Cloud top temperatures have cooled. Again, temperatures in the window channels at cloud top differ by about 2 to 3 Kelvin, but note that the delta T values showing cooling are fairly similar within 0.4 Kelvin. Cloud optical depth, COD, is a baseline product computed using different algorithms in the day and at night. The daytime algorithm is the only one available in AWIPS. The temporal cadence and horizontal resolution for COD are shown. Note that COD is not produced for AWIPS in mesoscale domains. It is computed up to a satellite zenith angle of 65 degrees using the visible band 2, 0.64 micrometers, and the cloud particle size band 6, 2.25 micrometers. The algorithm also requires cloud mask, cloud phase, and cloud height as inputs. The product is similar to the aerosol optical depth that is computed in the absence of clouds, and it's used to estimate cloud thickness, icing threats, and precipitation. Cloud particle size considers all pixels identified as clouds by the cloud mask. Cloud particle size represents the cloud droplet distribution. This is a baseline product. This daytime-only product is computed for every full disk, CONUS, and meso image. The full disk product has 4 km resolution, and the CONUS and meso domains have 2 km resolution. It is computed using the visible channel band 2 at 0.64 micrometers, and the cloud particle size channel band 6 around 2.2 micrometers. If you combine cloud particle size with cloud optical depth, you can estimate the cloud mass. Also, large water droplets and boundary layer clouds will likely be precipitating. Let's switch topics to discuss fog in low stratus. A nighttime method for identifying low clouds involves the brightness temperature differences between the window channel, 10.7 micrometers on legacy GOES, or 10.3 micrometers, band 13 on GOES R-ABI, and the shortwave infrared channel on both, 3.9 micrometers. Clouds made of water droplets are not blackbody emitters of 3.9 micrometer radiation. Thus, brightness temperatures computed from the radiance sensed by the satellite, a computation that assumes blackbody emissions, will be colder than reality. In contrast, clouds made of water droplets are more nearly blackbody emitters at wavelengths around 10 or 11 micrometers, so the computed brightness temperatures of those wavelengths are closer to reality. Taking the difference between the two values highlights clouds made of water droplets, that is, stratus. That's shown in the color enhancement, and also in the inset using legacy data that shows a cross-section from fog to cirrus. Computed brightness temperatures between shortwave and longwave wavelengths are different because of these emissivity differences. Note that cirrus temperatures are different as well because of subpixel effects that have been described in other satellite foundational courses for GOES-R. The problem is stratus and fog can look very similar from the top of the cloud deck. It's very hard for the satellite to view the cloud base. Because mid-level stratus is not an important aviation hazard, not usually, the aviation-focused IFR probability field shown here was developed to screen out regions of mid-level stratus and highlight only regions of fog on the ground. That product is shown here over Texas. In regions around Dallas, where the brightness temperature difference product on the previous page had a strong signal, IFR probability is low. That's because IFR probability incorporates model output. If the model output does not show low-level saturation, then it's unlikely that there is fog present. IFR uses this rapid refresh data to screen out regions of not interesting mid-level stratus and allow a forecaster to direct more focus to a potential transportation hazard. Brightness temperature difference fields cannot detect low clouds in the presence of cirrus, because emissivity differences of the low clouds aren't apparent to the satellite when cirrus blocks the view. In those cases, an example of which is shown in Louisiana, model data can provide information about low-level saturation even when satellite data are incomplete, and alert a forecaster to the potential presence of reduced visibility. IFR probability on the previous slide is not a baseline product, but it is a future capability product. A list of all baseline and future capability products is available at the link on this page. There are other supplemental links on this page for more in-depth information on these products. This concludes the GOES-R training on cloud products and fog detection. Thank you for listening.